3 major earthquakes, 3 different countries. 57 days. Venezuela, Colombia, Peru, all hit in under 2 months in the middle of 2026. Here is the full timeline, the plate mechanics behind it, and what scientists are saying could come next. On June 24th, 2026, at 6:04 in the evening local time, a magnitude 7.2 earthquake struck the region west of Caracas, Venezuela. 39 seconds later, a second earthquake hit. Epicenter, magnitude 7.5, the strongest to hit Venezuela in over a century. Both quakes triggered USGS red pager alerts, the highest warning level the system issues for expected casualties and damage. As of August 2026, more than 6,500 people are confirmed dead. Around 226,700 people were injured or hospitalized. Tens of thousands remain missing. NASA satellite analysis identified roughly 5,870 damaged structures. In La Guaira State, 80% of buildings collapsed. The twin quakes were estimated to have wiped out around 6% of Venezuela's entire GDP in a single evening. The UN put total damage at $37 billion, in a country whose economy was already in crisis before the ground moved. Search and rescue teams came in from France, the United States, including elite urban rescue units from Fairfax County, Virginia, and Los Angeles County, Mexico, and several other nations. Teams were still pulling people from rubble weeks later. Here is the detail that matters for everything that follows. Venezuela's earthquakes did not come from the Nazca Plate. They came from the boundary between the Caribbean Plate and the South American Plate in the north of the country. This is a strike-slip boundary, meaning the two plates grind horizontally past each other, like 2 slabs of rock being dragged in opposite directions. That motion produced 2 shallow, devastating ruptures, both under 20 kilometers deep, which is why the shaking at the surface and the destruction were so extreme. The Caribbean Plate did this, not Nazca. So why does the Nazca Plate matter to this story at all? Because the story didn't stop in Venezuela. 47 days after Venezuela, while search and rescue teams were still working through the rubble, while families were still waiting to learn whether relatives were alive, the ground moved again. This time, it was Colombia. On August 10th, 2026, a magnitude 7.4 earthquake, revised to 7.5 by the Global Centroid Moment Tensor Project, struck near the town of San Jose del Palmar, in the department of Chaco, in western Colombia. It was felt across all of Colombia, into Ecuador, into Panama, and into Venezuela, which was still actively conducting search and rescue operations from its own disaster. The Colombian Geological Survey confirmed it was the strongest earthquake in the country in the last decade, and the strongest since the 1979 Tumaco earthquake. More than 300 people were killed. Over 4,600 were injured. 425 people remain missing. The quake caused serious damage to hospitals, the airport, and thousands of homes across cities, including Cali, Pereira, Manizales, and Buenaventura. This is where the Nazca Plate enters the story directly. According to the USGS event page for the August 10th Colombia earthquake, the rupture occurred within the subducting Nazca Plate itself, as it dives eastward beneath South America along the Ecuador-Colombia trench. This is a key distinction. It was not a surface fault in Colombia that snapped. It was the Nazca Plate, deep underground, being torn apart by the pressure of subduction. A smaller fragment of the plate, often referred to as the Malpelo microplate, is currently moving east relative to South America at a rate of roughly 58 millimeters per year. That continuous, relentless movement is what generated the energy that killed those 300 people in Colombia. This is what makes the Nazca Plate different from a typical fault system. It doesn't just produce earthquakes at its edges, it produces earthquakes from within itself. The internal stress of being forced underground at speed fractures the plate from the inside, and those interplate ruptures can be just as deadly as the classic subduction boundary earthquakes people usually picture. Then came Peru, 10 days after Colombia, on August 20th, 2026. This was the event a seismologist had actually flagged in advance. Not the exact date, not the exact magnitude, but the location. The day after Colombia's earthquake, a seismologist publicly said he was tracking a pattern moving southward down the continent's edge and named Peru as the most likely next location. On August 20th, that warning became reality. USGS measured the quake at magnitude 6.7. Peru's own Instituto Geofísico del Perú measured it at 7.2. The epicenter was in the Ayacucho region, roughly 19 kilometers deep, inside the subducting Nazca Plate. Because of that depth, the energy had much further to travel before reaching the surface, which is why the destruction was dramatically lower than Venezuela or Colombia. 2 people were injured. Homes were damaged in the Ayacucho region. About 2.4 million people felt the shaking. There were no confirmed deaths. Peru got lucky, and scientists were clear about that. This was not a release of the region's main accumulated energy. This was described as a warning knock on the door. Here's the number that should get attention. Seismologist Cesar Jimenez Tintaya, a professor at Peru's National University of San Marcos, told the news agency UPI that only about 20% of the energy that has been building along Peru's central coast since the massive 1746 megathrust earthquake has actually been released. That means roughly 80% of the accumulated stress is still sitting underground, waiting. Based on that, Jimenez said a magnitude 8.5 to 8.8 earthquake could strike central Peru. A magnitude 8.8 would be roughly 250 times more powerful than the 7.5 that devastated Venezuela. To put 1746 in context, a magnitude 8.6 earthquake completely destroyed Lima, which had a population of around 50,000 people at the time. A tsunami struck 30 minutes later with waves reaching 24 meters. The entire central Peruvian coast was wiped out. That was the last time this section of the subduction zone released its stored energy at full capacity, and it happened 280 years ago. Today, Lima has 11 million people, many of them living in poorly constructed buildings on soft, alluvial sediment, the kind of ground that amplifies shaking dramatically. This stretch of coastline is known as the Lima Seismic Gap, one of the most studied and most feared geological features on Earth, and scientists say it is still almost fully loaded. Fabiola Barona, executive director of Peru's Intergeographic Foundation and an expert in disaster risk and climate change, told UPI that the zones of greatest concern along the Nazca South America boundary right now are southern Peru, northern Chile, Ecuador, and southern Colombia. She was clear that scientists still have no way to predict timing. She was equally clear that the physics of the situation is not in question. The plates are coupled, locked together, and deformation has been accumulating along those stretches for decades, in some places for centuries. It's worth sitting with what a red pager alert actually means before moving on. USGS doesn't issue that designation lightly. It's reserved for events the agency's automated models estimate could produce more than 1,000 fatalities and damage exceeding $1 billion. Getting 2 red pager alerts within 39 seconds of each other at nearly the same location is exceptionally rare in the modern instrumental record. It effectively meant the system was telling responders, before any human confirmation had come in, that this was already one of the worst earthquake events of the decade. That's part of why the international response mobilized as fast as it did. The alert level itself triggered protocols that don't normally activate for a single M7 event. This brings up the question people keep asking. Is there a chain reaction happening? Is the Nazca Plate triggering these earthquakes in sequence, like dominoes falling southward down the continent? The honest answer is that this is genuinely disputed within the scientific community. Stress transfer between fault segments is real and well documented. When one section of a fault system ruptures, it redistributes stress onto neighboring sections, releasing pressure in one area and potentially increasing it in another. That's accepted seismology, not a fringe idea. But Venezuela's quakes came from the Caribbean plate, geologically separate from the Nazca system. Arguing for a direct causal chain between Venezuela and Colombia requires seismic stress to travel through a complex tectonic boundary and then trigger an entirely different type of rupture, hundreds of miles away, inside a completely different plate. That is a hard case to make with the evidence available. What can be said with confidence is that the Nazca Plate is the common thread running through Colombia and Peru. It pushes against the South American plate at a rate of 6 to 8 centimeters per year, according to geological data from the Servicio Geológico Colombiano. That sounds slow, and it is. The fingernail grows faster. But it never stops, and it has been happening for millions of years. The Andes mountain range, the longest continental mountain range in the world at roughly 7,000 kilometers, exists entirely because of this ongoing collision. Every mountain in the Andes is a record of the Nazca Plate pushing the South American plate upward. Every locked section along that subduction zone is stored energy waiting for release. The Nazca Plate sits on the Pacific Ring of Fire, on the horseshoe-shaped belt of tectonic activity around the Pacific Ocean, responsible for roughly 90% of the world's earthquakes. It is an oceanic plate, denser than the continental crust of South America, which is why the two don't collide head-on. Nazca is forced to dive underneath. As it descends into the mantle, the process isn't smooth. The edges are rough, the plates lock together, pressure builds over decades and centuries, and then it releases all at once. Picture bending a thick steel rod slowly. As pressure is applied, nothing visible happens for a long time. The rod is storing the energy elastically. You can keep bending it, and then, without a precise warning sign, it stops bending and breaks, releasing all that stored energy in an instant. That is essentially what happens along a locked subduction zone. The geological record along South America's western coast is a history of this exact process repeating over and over at different points along the boundary, across thousands of years. The 1960 Valdivia earthquake in Chile, magnitude 9.5, remains the most powerful earthquake ever recorded anywhere in the history of seismology. The 2010 Chile earthquake, magnitude 8.8, was the same process. The 1970 Peru earthquake, which triggered a landslide that buried entire towns and killed tens of thousands of people, was this process. The 1906 Ecuador-Colombia earthquake, magnitude 8.8, still one of the largest ever recorded instrumentally, was this process. It keeps happening because the Nazca Plate keeps moving, and there is no geological scenario in which that stops. It also helps to understand why the 1960 Chile earthquake gets brought up so often as the reference point for worst-case scenarios. That event, magnitude 9.5, ruptured roughly 1,000 kilometers of the Chilean coastline in a single event and generated a tsunami that crossed the entire Pacific Ocean, killing people as far away as Hawaii and Japan, more than 10,000 miles from the epicenter. It remains the single largest release of seismic energy ever measured by modern instruments. The reason seismologists keep referencing it isn't nostalgia for a disaster. It's that the same subduction mechanism that produced it is still active along the entire length of the coast, from southern Chile up through Peru, Ecuador, and Colombia. The 1960 event didn't happen because that stretch of coastline is uniquely cursed. It happened because that's what a fully locked, centuries-old segment of a subduction zone does when it finally lets go. The concern about central Peru is built on the same logic, applied to a different segment of the same boundary. There's a concept driving a lot of the concern among seismologists right now that doesn't get much media coverage: seismic gaps. A seismic gap is a section of a known active fault system that hasn't experienced a major earthquake in an unusually long time. Because the fault is known to be active and accumulating stress, a long silence doesn't mean the area is safe. It means stress is building. Statistically, the longer the silence, the larger the eventual rupture tends to be. Scientists identify these gaps by studying the historical earthquake record along the boundary, where events happened, at what magnitude, and when. What they found along the South American subduction zone is concerning. Several major seismic gaps, though, remain largely unruptured. The Lima Gap is the most discussed. The central Peru subduction zone last fully ruptured in 1746. Since then, there have been partial releases, a magnitude 8.2 in 1940, and a handful of magnitude 8 class events in the decades that followed. But seismologists emphasize these only released a fraction of the total accumulated energy. The gap is not closed, it's still open, and Lima, a city of 11 million people, sits directly in its path. Peru's National Center for Disaster Risk Estimation classifies the Lima area as facing a very high level of seismic risk. Not moderate, not high, but very high. Southern Peru and northern Chile carry a related concern. That stretch of the subduction zone produced major earthquakes in 1604, 1868, and 2001, but sections of it remain under stress. Ecuador and southern Colombia, which just experienced August's major event, sit above one of the most actively deforming areas on the continent, and that 58 millimeter per year movement isn't going to slow down. Building quality across South America is what turns geological risk into human catastrophe, and Venezuela's disaster made that brutally visible. Entire residential towers collapsed. Whole neighborhoods in La Guaira state were simply gone. Part of that is the intensity of two near-simultaneous shallow earthquakes. Part of it is that Venezuela's construction standards, particularly in coastal areas, hadn't been enforced or updated in decades. Colombia saw a similar pattern: hospitals damaged, an airport with structural failure, thousands of homes not built to withstand this level of ground acceleration. Peru has taken earthquake preparedness more seriously since the 2007 Pisco earthquake, a magnitude 7.9 that killed nearly 600 people. But Lima's housing stock remains deeply vulnerable. The city expanded rapidly over the last 30 years through informal construction, meaning millions of homes were built without permits, without engineering oversight, and without seismic reinforcement. When a magnitude 8.5 or 8.8 event reaches Lima, and the science treats this as a matter of when, not if, the scale of destruction could exceed everything seen in South America so far in 2026. The human side of this is easy to lose in the numbers. Venezuela's earthquakes happened during a period when the country was already dealing with years of economic contraction, hyperinflation in earlier years, and mass immigration. Millions of Venezuelans had already left the country before June 24th. That backdrop matters because it shaped how the disaster response unfolded. Hospitals that were already understaffed and undersupplied were suddenly handling mass casualty events. Infrastructure that hadn't been maintained in years was the infrastructure people needed to survive on. In Colombia, the affected departments in the west of the country are among the regions with historically less investment in public infrastructure compared to Bogotá and the country's economic centers, which is part of why hospital and airport damage in Chaco had such an outsized effect on the emergency response. There wasn't a deep bench of nearby unaffected medical capacity to lean on. None of this changes the geology. It changes what happens to people when the geology does what it does. There's also a technological angle here that doesn't get much attention. South America does have seismometer networks. Peru has implemented SASPE, the Sistema de Alerta Sísmica del Perú, designed to send alert messages to areas within a defined distance of an epicenter for earthquake's magnitude, 6.0 and above, triggered within seconds of the P wave arriving at the nearest station. That's genuinely impressive early warning technology. But, as Venezuela and Colombia showed, early warning gives seconds of notice, not hours or days. It's enough time to drop and take cover. It is not enough time to evacuate a city. Despite advances in machine learning and satellite-based ground deformation monitoring, scientists still cannot say which month or year the Lima Gap will close. They can measure how the ground is deforming. They can calculate probabilities. Exact prediction remains, as of August 2026, an unsolved problem. Here's the full picture as it stands in late August 2026. In under 2 months, South America experienced a magnitude 7.2 and 7.5 seismic doublet in Venezuela, a magnitude 7.4 to 7.5 in Colombia, directly attributable to the subducting Nazca Plate, and a magnitude 6.7 to 7.2 in Peru, deep within the Nazca Plate itself. Over 6,500 people confirmed dead in Venezuela, with that number still not finalized. Over 300 dead in Colombia, hundreds still missing. Billions of dollars in Inaudición, damage across 3 countries, millions of people displaced. The discrepancy between USGS's 6.7 reading and IGP's 7.2 reading for the Peru event highlights how differently measurement methodologies can characterize the same earthquake, even with modern instrumentation. What both agencies agree on is where it happened, deep inside an actively subducting plate. And what seismologists agree on is that this was not a release of the big stored energy. The central Peru seismic gap is still estimated at 80% capacity or higher. The scientists tracking this aren't being alarmist for effect. Barona was clear that timing cannot be predicted. Jimenez was clear that he was describing accumulated energy potential, not making a specific forecast. But the pattern across 2026 has put the scientific community on heightened alert because 3 major events in under 2 months, all within the same general tectonic system, all marching southward down the Andes corridor, is not random background seismicity. Colombia, Ecuador, Peru, and northern Chile are the regions seismologists say need to be watched closely right now. It's also worth being precise about what prediction would even mean, because the term gets used loosely. Seismologists are not close to being able to say an earthquake will happen on a specific day, and most in the field are skeptical that kind of precise short-term prediction will ever be possible, given how chaotic the physics of fault rupture is at the point of failure. What they can do, and what they are doing along this stretch of coastline, is closer to actuarial work than prophecy, measuring how much strain has built up in a locked segment, comparing it to the historical rupture record for that segment, and estimating a probability range for a large event over a multi-decade window. That's a fundamentally different kind of statement than an earthquake will strike Lima in the next year. It's closer to how insurers model flood risk or wildfire risk, not certainty about a date, but a strong statistical basis for treating a given decade as meaningfully higher risk than average. That distinction matters because it's the difference between science-based risk communication and fear-mongering, and it's worth holding on to whenever headlines about the next big one start circulating. What can actually be done is preparation. Building codes can be upgraded and enforced. Existing vulnerable structures can be retrofitted or demolished. Emergency response plans can be rehearsed. Tsunami evacuation routes can be marked and practiced. Public education on drop, cover, and hold procedures can be expanded. Supply caches can be prepositioned. The difference between a natural disaster and a full catastrophe is often not the earthquake itself. It's the state of preparation that existed before it hit. Japan experiences earthquakes as powerful as anything South America faces, and its death tolls are typically a fraction of what's being seen from comparable events here. That difference comes from infrastructure and preparation built over decades of deliberate policy. The Nazca Plate will not wait for that preparation to be completed. It does not check whether Lima's informal settlements have been upgraded. It moves at 6 to 8 centimeters a year, has been moving for millions of years, and will keep moving long after everyone alive today is gone. The only variable is how ready the people in its path are when it speaks again at full volume. So where does this leave things right now? Venezuela is still in crisis. Colombia is still counting its missing. Peru just felt a warning tremor from 99 kilometers underground. Scientists are publicly warning of a potential magnitude 8.5 to 8.8 in central Peru. an event that would be roughly 250 times more powerful than what destroyed Venezuela. Lima, a city of 11 million people, sits almost directly on top of the most loaded seismic gap in the Western Hemisphere. Ecuador and southern Colombia are flagged by multiple experts as being under elevated stress. Northern Chile, which produced the greatest earthquake in recorded history in 1960, is being watched carefully. The western edge of South America has, as multiple seismologists have said publicly in the past 2 weeks, been reminded 3 times in 2 months that it sits on one of the most active fault systems on the planet. The Nazca Plate is not finished. The energy is still there. The gaps are still locked. And somewhere along that 7,000-kilometer corridor, the next rupture is already building. The only thing not yet known is which section gives first.